Okay, good morning. Today I'm presenting joint work with my supervisor, Ulrich Buchholz, and it's on geometric type theory. Not what it is, because it doesn't exist yet, but what it should be, I think, and why I think you should care about it. So what's the setting? We've got several generalizations of spaces. We start with topological spaces, and we can look at the frame of opens of that space. And this frame of opens actually forms a complete Heiting algebra. So we've got infinite joints, we've got exponentials, intersections, top element and the bottom element. And so we can view this as a space to the logic. We can view it as a model for some propositional theory, which is higher order. But a continuous map between two topological spaces doesn't preserve all of that. Continuous map only preserves infinite joints, but not infinite needs, and in general also not exponentials. So we could say that the geometric fragment of this logic that happens inside the frame of opens is that fragment of the logic which is preserved by that inverse image part of continuous map. And pretty much the same thing happens in the category of locales. So if we have a topological space, we get this frame of opens, okay? And a locale is pretty much presented by a frame. Continuous maps between locales also preserve the same structure as continuous maps between topological spaces, which is, again, not everything that really goes on in a frame. And generalizing further, we've got toposes, so locales embed fully faithfully into the category of toposes, and that's a straight generalization. And if we view a topos as a category, so as a logos, then internally we can interpret Martin-Wolf type theory. We've got universals, we've got sigma types, pi types. But once again, the logic that happens internally in the topos isn't fully preserved by a geometric morphism, which is a morphism in the category of toposes. And the fragment of the length of the logic that is preserved is called geometric logic. Yeah, and the same thing happens in infinity toposes. We can model hot in infinity toposes, but the general infinity geometric morphism doesn't preserve all of that. So we would like to pay some more attention to what's geometric and what isn't. And then there's one more fact that we base this talk on, and it's that toposes are classifying toposes. So there's a notion of geometric theory, which is an infinitary first order logic over some first order signature. And for every such theory, there exists a topos which classifies it, meaning that the model of this theory in the topos E corresponds to a geometric morphism into that classifying topos. And conversely, every topos classifies some geometric theory. Okay. And it was Stephen Vickers who, to the best of my knowledge, first suggested that this is reason enough that we should define some type theory in which types behave like toposes. And okay, here are a couple more reasons why we might care about that. So I've already mentioned that some results are not preserved. So if we prove something internally in one topos, if we can recognize that that thing is geometric, we can also know that it happens, that it's true in every other topos, which has a morphism into that. Sometimes we also care about non-geometric statements. For example, in synthetic algebraic geometry, we've got non-geometric statements, which we use to actually talk about what happens in the Zariski topos. And these are important too. We want to recognize when a statement is not geometric. Because we can also use non-geometric statements to derive statements which are geometric again, and these will be preserved again. And then in general, as it often happens in topos theory, we have to switch between the internal and the external perspective. Anyone who does synthetic mathematics knows that it's nice to work internally, but you still have to justify externally that what you're talking about internally is actually what you want to talk about. And we've got several different use cases of that synthetic algebraic geometry. synthetic differential geometry and synthetic Tate commutability. All of that requires going back and forth between the internal and external language to sort of get the full picture. Mark has also spoken about modalities. That is true. We would like to know how they behave if we go from one topos to the next one. In general, if we're given some topos as a category, it's also hard to come up with a geometric theory that is classified by that topos. We can sort of do the whole internal language thing and construct a geometric theory which will classify, but it won't be very nice and not very natural. It will be very large. So maybe we can find nicer presentations there. Another thing is the bridges that come up in Olivia Caramello's book, where we mostly care about constructing equivalences between toposes, and there one has to be creative too. But if your toposes are presented as types, then it might be easier to come up with such equivalences. And then finally, we've got this nailed down for one toposes. Maybe the situation in an infinity topos will be a bit more clear. So in an infinity topos, we don't really know what an infinity geometric logic might even look like. We know that all infinity toposes arise as left exact accessible localizations of a pre-sheaf infinity topos, but that doesn't tell us anything about a good syntax of the geometric fragment internally. And last but not least, if we've got a type theory, we can formalize things. Not so nice. Okay. Now there's a bunch of work that deals with this problem, but in my opinion, none of that really addresses everything that we would want in a geometric type theory. So none of these points use all toposes or use the universal property that a topos is a classifying topos for some theory, or straightforwardly extend hot, something like that. Okay. I'm not going to go through everyone, but if you have questions, I'm happy to talk about that. Okay. So I think a good approach to modeling geometric type theory is to take the brute force approach of taking the whole category of toposes, which is a 2-2 category. We forget about the non-invertible two morphisms and define some topology on that and take sheaves on that. And of course, there are genuine size issues here. We're taking sheaves on a large collection of objects, which are categories, which are itself large. But let's not talk about size issues here today. Assuming this works, then we can represent a specific topos in our internal language, and that is the theory of an object. So this classifies the geometric theory of just one sort, no function symbols, no relations, no axioms. And a model of this theory, aka a morphism from E into O, is exactly an internal object in E. So a sheaf, which as a topos corresponds to the slice topos of E at the object X. And let's just denote that T of X. Oh yeah, the upper right corner of the polar X square is of course the theory of a pointed object. We just add a point to our theory of an object. And if we've got this, we can recover a lot of things. We can recover functions internally. We can also recover the Sierpinski space. So in this language, the Sierpinski space just assumes that we have a sort. And that sort is a proposition. Okay. Now that was my first approach to, well, not really my first approach. I went through all of this. But that was my first serious attempt at defining geometric type theory. But with all the size issues, with all the universal properties and everything going on, I decided maybe it's easier to first look at the propositional case. So propositional geometric type theory should be modeled by objects which behave like spaces which classify propositional geometric theories. So we don't have sorts, we don't have function symbols. We only have propositions, subterminal objects, and relations between them. And the category of classifying spaces for that is exactly the category of locales. And there, the topology which we should be using is a bit more clear as well. We use the open cover topology. So yeah, a locale is covered by a collection of opens which are jointly surjective. And locales are, well, a poset enriched one category. We forget about the poset enrichment, get one category, and just take sheaves on that. Size issues still persist, but it's a bit more tangible. And the main base type we make synthetically available in our theory is the Sierpinski space. So yeah, open cover topology is subcanonical. All locales are faithfully represented in our theory. We take the Sierpinski space. This has an open point, and pulling back along that open point gives us exactly an open sublocale, which I call TFP of the locale A. Yeah. So what else have we got in our syntax? We assume intentional MLTT, make sure not to use UIP. So we're agnostic to the infinity topos setting. S syntactically behaves like a Tarski style universe, but it's not closed under pi types in particular. We primitively assume top and bottom elements as closed as global sections of the Sierpinski space. And pulling back along the open point does nothing. We get the terminal object. Pulling back along the closed point gives us the empty space. And now we also need something to access the structure that's actually present in a locale. So we primitively assume that we have binary conjunctions. That gives us the order relations, the order relation on the opens of a locale. And then we can have a whole bunch of axioms that makes this into a meet semilattice with the top and bottom element. But of course, we also need infinitary disjunctions. How do we get them? The process here is pretty standard. We define what it means for a map to be open. That's exactly when its inverse image part has a left adjoint. And then a type I is called overt if the terminal map is open. And the overt types are exactly the ones over which we allow infinitary disjunctions. And then we can actually assume that our locale S is a frame with respect to these infinitary disjunctions. And then we've got a couple more things we can do already. We can say when a type is discrete. When the diagonal is open, this is a standard definition as well. And we also assume that the natural numbers are discrete and overt, and the Sierpinski space and the open subtypes of the Sierpinski space are overt, but not discrete. And yeah, we can also prove that being overt discrete is closed under positive type formulas. So sigma types, identity types, coproducts. Yeah. And we can also characterize the opens of an open subtype. So if we have an open subtype P determined by some proposition P in the context, then the opens of that corresponding subtypes are just the propositions which are smaller than that, which is nice. Okay. Now there's something I stole pretty much from condensed type theory. And that is those overt discrete types satisfy a directed kind of univalence. So a map, if A and B are overt discrete, then maps between A and B give rise to a kind of directed path in the universe of overt discrete types by evaluating a map out of the Sierpinski space at at the bottom element and the top element. And for overt discrete types, this map is an equivalence in condensed type theory. This is called directed univalence. And it should hold here because condensed sets sort of approximate topological spaces as a topos. And they also faithfully contain overt discrete locales. Okay. Yeah, and what's interesting about this is that we can actually write down a map in one direction. So if we've got some F, we can look at the total space of the join of the fiber at some point with the open, with some point of the Sierpinski space. So essentially, maps between overt discrete spaces are those which can be recovered by looking at the closed modality corresponding to some opens. If we know that for all opens, we can recover the whole map. Okay. Now that's where I'm at. There are still a couple of things to do to make this actually useful. And the main thing is that we care about the topology of function spaces. So the third bullet point states a result which is true for locales. So if we have the locale of natural numbers and the locale of the Booleans, then this equivalence holds. That's one of the funny things of point-free topology. And well, we represent locales faithfully, so this should also be true in our topos. We can write down the maps in both directions, but we still need some extra conditions that actually lets us prove that this holds. And current ideas are to use the synthetic quasi-coherence axioms or the local choice axioms that come up in synthetic algebraic geometry, because they pin down the topology of our base spaces. Okay. Then it might also be interesting to investigate the simplicial aspects a bit more, to ask, okay, what are the complete Siegel spaces with respect to the Sierpinski space in other types, not just the type of overt discrete types. And of course, my main goal is not to talk just about locales, but actually to extend this to full geometric type theory. Okay, and that's it. I hope you learned something. The rest of the slides are just references. Thanks.
Can you say maybe a bit more about the difficulty would be in extending this full geometric type theory?
Yeah. Okay, the main difficulty is that there are so many options, so many decisions you have to make, and it takes a very long time to check if that actually works. I guess in locales, we don't really care too much about the internal exponentials in the frame of opens. But in toposes, this is more present. So there are two ways of going about this. One is to add a modality, which gives you access to the full internal language. That is not really clear about how this modality should be defined globally for all toposes, and it's syntactically complicated. The other difficulty is if you don't want to add the modality, then you have to come up with actual sheaves on your side which are not representable, which faithfully recognize that what you're doing internally is not geometric, but is still substitution stable. So you need to know how this evolves if you pull back along the geometric morphism. Yeah, it's just a lot of things to look at once.
Yes, I was actually going to ask about those modalities that that let you talk about the inside of a topos in a very much the same way that adding something to your context lets you talk about things happening in a slice topos. I was looking at the notes of Stryker, I believe, on characterizing geometric morphisms as in terms of their stack that they present of toposes and logical morphisms. And it seems like that would be like a good guide to figuring out what those geometric modalities would do. Have you seen that?
Okay, no, I have not looked at that, but I will. Yeah, thank you for that. I mean, if it only uses logical morphisms, then that's a bit too strong. But yeah, I just have a look at it. Thanks.
Well, yeah, it uses logical morphisms as the transition maps in the stack, but it represents geometric morphisms.
Right. Okay, yeah, that could be nice. I'll have to read the paper.
So, is it possible in this theory to recover the stuff on the previous talk, like the construction of sheaf and so forth? Let's say we have some topos and we have some propositions, and can you form like the sheaves in that topos with respect to this proposition somehow?
It should be, but I only started thinking about this yesterday, so I'm not quite sure. Yeah.
If the geometric type theory should be some kind of type theory where types behave as toposes or topoi, there's some kind of connection to some kind of directed type theory where like types are actual categories. It's like some directed type theory, but with more accents, maybe. Because you have also this directed univalence.
Yeah. So you do get the simplicial aspects by mapping out of interval objects. It's directed in that sense, and it's also kind of directed in the sense that mapping into the object classifier or mapping into any topos gives you a whole category of models in your domain. But it's really not clear to me what a univalence principle should look like in that case. Because those categories could be a whole topos, but they could also be not very nice. I don't know.
Thanks. Okay.
I have a question. I don't know if you can hear me. Can you hear me? Yes.
Yep.
Solid. So this is fairly conjectural, but well, your thing is, what do you think there's a relationship to some proposition for geometric homotopy type theory that could be compatible with your framework? And I know all of this is conjectural, and there's not an established definition of any of them, but I'm curious.
Sorry, could you repeat the question? I'm not sure I
Yeah.
understood.
Yeah. So you're talking about geometric type theory. I'm curious whether your construction is I'm actually curious about two things with regards to this construction. But first, do you think that do you have like a conjectured version of your construction or of something that would be related to it that would give you something that would play the role of a geometric homotopy type theory? And this time, I mean, we're talking about infinity versions of everything.
Yeah, I mean, my hope is that we can sort of extend this to sheaves on the category of infinity toposes, viewed as infinity one category, just by transferring the appropriate universal properties rather than looking again syntactically at what should be an infinity geometric logic. And I want to see how far I can get with that once the geometric theory for the one case is established. Yeah, but that's my hope.
Cool. Thanks.
More questions? On the last slide, you mentioned synthetic quasi-coherence, and I was wondering what exactly it looks like in this setting.
Yeah, okay, so it should be the case that if X is actually represented by a locale, then the precomposition map, or I guess the evaluation map, going from X to the spectrum of X, which in this case is just the frame of opens of X, to the Sierpinski space, is an equivalence. Yeah.
So we're slightly ahead of schedule, I think, but finish it. Thanks again. Thank you.